this example, we'll look at how Solid Edge's embedded CFD tool, FlowEFD, can be used to analyze a flow and thermal management problem of a new audio amplifier to ensure that it meets consumer electronics standards for temperature distribution. First off, notice that with FlowEFD directly embedded in Solid Edge, we get a consistent look and feel to familiar Solid Edge capabilities such as structural simulation. As we set up the problem, we'll utilize the new ribbon and edge bar options to manage all of the study details. The most convenient way to create a project is to use the wizard, which guides you through the setup of the basic definition of the analysis. Following the step-by-step guide, from project naming to the type of flow study to be analyzed, the wizard is an easy first step to get started. To begin, we'll set up our initial conditions, the default material used on the majority of the model, and the type of fluid and flow that it'll be experiencing. All other specific details we can assign directly on the 3D geometry making up the assembly. One of the great aspects of having FlowEFD embedded directly in Solid Edge is that visualizing studies and results is simple, as you can see and select the exact components necessary using native geometry. In the wizard, we set a generic material of aluminum for the parts in the assembly. But now let's look at specific components of note. Our key areas of heat concern and generation is the PCB and the transistors. First off, the PCB. As printed control boards have many layers of conductive material sandwiched between insulation layers, we need to be specific on the type of material used. Using a pre-delivered list of common materials, we can quickly set it to a predefined 9-isotropic PCB with 8 layers, and then set the direction of the insulation in the Z-axis. Of course, if we have materials that are more commonly used, we can easily create a user-defined set. Once we've set the material for the transistors, we're ready to move on to boundary conditions. Since this study represents an internal flow of an enclosure cooled by a fan, we need to establish the boundary conditions of the casing. First, the vent slots where the air can exit the enclosure. When working with FlowEFD and Solid Edge, boundary conditions are represented by geometry called lids. Our first set of lids represent these vents, an environmental pressure opening, allowing the air to move freely between, depending on the pressure inside or outside of the casing. For our next boundary condition, we need to represent a fan forcing air through the enclosure. Once again, using a lid as a geometric representation, we can define what type of airflow will be established. We'll use one of the predefined fans for an easy representation of off-the-shelf components, containing all of the essential properties needed for a flow study. A couple of additional settings for the rotations and the airflow, and our boundary conditions of this enclosure are complete. In addition to how the air will flow through the casing, we also need to see how the temperature will be distributed. Our next step is to set up the sources of heat on the assembly. Once again, we'll be focusing on the PCB and transistors. FlowEFD and Solid Edge makes geometry reselection simple. As we've defined each of these components previously with specific materials, we can simply reselect that representation in the edge bar and the same geometry is automatically selected. For heat generation, the transistors will be generating 20 watts in total, with the PCB generating 220 watts. Finally, let's set up some goals that we want to meet with the study. If we have particular items or components of interest that we're focused on, we can use them to establish goals. Here, we want to know the average and maximum temperature the transistors will reach, as well as the eventual flow rate of the fan cooling the enclosure. These goals not only give us a nice readout of the focus of our results, but also gives the parameters the study will use so that it can converge and solve. As we'll see in a few minutes, goals are also a great way to do comparisons between different study configurations, offering side-by-side visuals to find optimum results. Now that we've got our study parameters and goals defined, let's take a look at the mesh settings. One of the core strengths of FlowEFD, which overcomes long-standing bottlenecks in traditional CFD processes, is its meshing approach. This approach uses cutting-edge meshing technology to cut the amount of time building the mesh considerably. With both simple controls of mesh fidelity as well as more complex advanced meshing options, FlowEFD can mesh a wide range of complex geometry, giving proper results whether you're a design engineer or an analyst. Now that we have the study set up, it's time to run the analysis. FlowEFD in Solid Edge allows users to determine which computer or system they wish to run the solver on, as well as allowing the CAD to be separate from the solver activities, freeing resources to continue design work if necessary while it iterates. We'll take a look at the solving process in just a second, but while it meshes and gets started, let's take a look at the result outputs with some pre-run studies. While there are many ways to view the results of a study, we'll start by taking a look at some pre-configured plots. First, cut plots. Cut plots allow us to view slices of the study at any depth in the computational domain. Here, we can see the velocities and the temperatures as they relate to one another. Next, we have surface plots, determining exactly what the temperatures look like on the surface of components, such as the PCB. We can use the results bar to see that the center of the board is quite hot, over our limit, but if we want to see an exact value, we can easily do so using the probe tool, just like structural simulation in Solid Edge. Additionally, as we set goals in the study setup, we need to validate not only the PCB temperature, but the temperature of the transistors as well, ensuring that it doesn't exceed our allowable consumer electronics requirements. This can easily be accomplished by creating a goal plot to verify our targets are being met. Another great tool for viewing results is to use a flow trajectory. We can look at the velocity of the air and the flow as it comes through the fan. Here we can see the reason the center of the board is too hot is because the flow is staying mostly on the outside of the enclosure, not allowing for proper circulation through the center. Following inspection of the results, it's apparent some changes need to be made. FlowEFD and Solid Edge can clone any study, giving options to which configuration of components work best. In this case, we already have a second configuration set up, so let's take a look at how moving the fan over and extending the heatsink affects the flow and temperatures in the model. First, we use the PCB surface plot to see how much the temperatures cooled in the center of the PCB. Once again, using the probe tool shows us that we're now well within the boundaries of our consumer electronics requirements, and we can turn on the flow trajectory to see the change in the airflow through the casing. Of course, what if we have several different configurations available and we want to find the best solution? Using the Compare tool is a great way to customize the views of the outcomes between different studies. Any results created can be used for comparison, from cut, surface, and goal plots to flow trajectories or active scenes containing combinations of any of the above. Like all simulation studies, a concern is the amount of time and resource it takes to run. The great thing about Flow EFD and Solid Edge is not only can you run it while still doing CAD work, as we've been doing here, but the solver also has specific options to give you a nice visual of what values are being found while the study is converging on an answer. Not only can we view live readouts of values of our study goals, but we can also preview exactly how much of the enclosure has been solved, with an estimate on when it will be finished. A great piece of functionality to not only see the status of the study, but also to let you know if you're in the range of where you need to be. It's easy to see how Flow EFD and Solid Edge is a great addition to workflows, validating a design as it's modeled. With an easy-to-follow wizard for study setup, a comprehensive set of tools for study outputs, and state-of-the-art mesh and solver capabilities, Flow EFD is the perfect tool for design engineers and analysts alike.